So, good morning, friends. Today, I will discuss another important method for studying the fast reactions. I have already discussed about the flow method as well as the stopped flow kinetics. And you have seen that if a reaction whose half-life is 1 millisecond, that can be studied with the help of stopped flow technique. But there is a concept of the mixing. But suppose a reaction whose half-life is less than 1 millisecond. That means the range must be in between 1 millisecond to 1 microsecond. That means 1 into 10 to the power minus 6 seconds. Then of course, we have to avoid this mixing time or the mixing process because the reaction is occurred before the mixing. So for such type of the reaction, the relaxation methods are very useful. As you know that there are many good books of physical chemistry are available, but for fast reaction, I suggest to my student, please refer this chemical kinetics because I have referred this chemical kinetics by Ledler for some simple derivation of the relaxation kinetics. In addition to that, you can also refer, as I always told you, that this book is only for fast reactions. You will get all the methods, whether it is the NMR method or T-jump method or P-jump method, you can refer this book, Chemical Kinetic Methods. That means my today's lecture is based on these two books as well as some research paper. Now before I start this lecture, I must tell you the brief history of this relaxation technique because the great scientist, of course German scientist, Professor Manfred Eigen, at the age of only 40 years, that great scientist awarded Nobel Prize for studying these fast reactions. H plus OH reaction is equal to water. And in the year of 2019, he passed away. And then, of course, this is a very famous journal, Langue Chem International Edition. They have published research articles, and I'm just showing that article that one of the most important part is that the mixing system is bypassed. And suppose a reaction is just, if I write the fundamental concept of the relaxation technique, you all know that is the concentration and time, because we avoid this mixing of the reagent. So what we do, suppose this reaction is just normal under the equilibrium, suddenly in this relaxation technique we perturb or disturb that equilibrium. So there is a change in equilibrium and a new equilibrium is reached. So what I can do, this is a relaxation So by this perturbation can be done with the help of increasing the pressure, increasing the temperature, increasing the other electrical methods. So that is the fundamental concept of this relaxation technique developed by the great scientist Manfred Eigen. I have already discussed with you that this is the most important part, that if the reaction is 10 to the power minus 6 second, half-life of course, that reaction can be studied with the help of this relaxation technique, and you will be surprised to know that if the rate constant is approximately 1.4 into 10 to the power 11, you see just so fast reaction, very fast. Thank you. So it's a very fast reaction, of course, can be studied with the help of these reactions. And here we will not determine the half-life. In fact, we will determine a new concept. I will discuss what is that concept. That is called the relaxation time, tau value. Because when there is a perturbation of the equilibrium, so it relaxes that system. And during that relaxation process, the speed can be measured, of course. Concept is same, that whatever the change, that can be calculated with the help of spectrophotometry, that can be calculated with the help of the conductometric method. Now, this is the, I think although he has been awarded Nobel Prize in the year of 1967, as I told you, at the year of 40 years only. But he actually published the first paper on this first reaction in 1954. You must know some of the history of that most important reaction, that is the neutralization reaction, H plus OH is equal to water reaction. Very, very important reactions. And you see that the title of that, the first paper based on this H plus OH reaction, is the methods for investigating of ionic reactions in aqueous solutions with half times is 10 to the power 9 second. Can you imagine? Then of course this application to neutralization reaction and hydrolysis reaction, and after that he has done a lot of work in the biological system like DNA bindings and other things. But initially he was involved in this simple neutralization reaction. This is the first paper of this great scientist. And when he was awarded Nobel Prize, this is the actually original form of this reaction. When he was awarded Nobel Prize, as I discussed many times, that every Nobel laureate do deliver a Nobel lectures, and he or she discuss the whole story of these reactions. So that time when he started this work, it is really very difficult to measure such a fast reactions, because you know that the half-life or the rate constant is 10 to the power 11, like that, very, very high. And but of course he is able to discuss this thing, and he started these reactions, and therefore the title is immeasurably fast reactions. This is I have taken from this Nobel lecture, and this is actually this relaxation time. So this is the very simple history of the fast reaction. Now I will start the derivation and other things. Now actually in 1967, two other scientists, when I will teach the flash photolysis, then of course I will discuss the Norris and Porter work That is different thing. That is the plus photolysis. There is also fast reaction. But basically today I will concentrate only this water reactions and water formation of the water reaction, and if time permits, I will show some of the numerical problems related to this type of the reactions. And you see, I have already given that is very 1.4 into 10 to the power 11, like liter per mole per second. And if it is a deuterated, the formation of the D2O reaction also is also very fast reactions, 8.4, 10 to the power 10. So you must know, you must collect some example of other fast reactions. But this is very common reactions. Now, as you know that because the reaction is very fast, the most important part is that this tau value. So, if I determine the, suppose A is converted into B and this is K, this is K1, so I can calculate the relaxation time or vice versa. That means if you know the value of relaxation time and if you know the concentration of A, initial concentration of A and B, you can calculate the forward reaction as well as the backward reactions. And if you ask me, sir, what is the actual definition of relaxation time? After doing the derivation, I will explain the exact definition of the relaxation time. But you just imagine that there is a perturbation in the equilibrium and that system reached a new equilibrium. Now, if I want to return to the original equilibrium, so that type of that slot is actually relaxation time. And of course, the values of the relaxation time is depends on the rate constant forward reaction as well as the backward reaction. Now, if you refer most of the books, like again I am telling to my student that you must refer 3 books, like Physical Chemistry Atkins, and just open that chapter of the fast reaction. Physical Chemistry G.M. Barrow and Physical Chemistry Ira and Levine. You will find that there are 3 different types of numerical problems. Of course, dealing with the water system. But because we are all students, we have to learn other reaction also, like formation of carbon monoxide or the carbon dioxide reaction. That is also a fast reaction. So you will see that for each and every reaction, relaxation time is different because it is a characteristic of particular type of the reaction. So today I will discuss I will derive the relaxation time, and in a nutshell you can call it a reaction return to equilibrium. That is called relaxation time. The time during which the reaction gets relaxed from the equilibrium is called the relaxation time. Okay, it is a more general statement. And today I will discuss 3 types of reaction. First is, suppose A, many times I am showing you these things, A to B. Or I can write A is equal to B plus C. Or A plus B is equal to, both are reversible. Follow my point, reversible. But this is actually first order, sometimes it is a second order kinetics. Now, you must very careful while solving such type of the problem or the derivation. Now, if it is A, B, if I just want to calculate the tau value or the relaxation time, it is 1 divided by K1, K inverse 1. Now for this reaction, this is 1 divided by K1, 2, K inverse 1, XC like that. Now if it is 3, so this is 1. Don't cram it, I'll explain these things, everything. I'll explain A or A plus B like that. What I mean to say that without knowing the mechanism, it is very difficult to determine the relaxation time. So I am just using 3 reaction A, B, first order reaction A, B plus C, AB plus C. I am getting 3 different formula for relaxation time. So we should be very careful while solving the problem or derive the things. So first you write the mechanism or the system, then you can derive these things. I have already told you that now depending upon these types of the perturbation, the relaxation techniques can be classified. Relaxation technique can be classified like that. If it is perturbation is done by the temperature, we must have a capacitor and we discharge the electrical current. So it is called the temperature jump method. If I change the pressure, so generally it is very popular term like the T jump or P jump, and it is electric field, so it is called the E jump. So shortcut, you can call it T jump method, you can call it E jump method, you can call it T jump method, you can call it P jump method. Again, T jump method can also be subdivided. Suppose you are measuring the conductance, so there is no hard and fast rules, you can measure the conductance. You can measure the optical density like that. So it is, but basically there are three methods basically. And if you see some of the good literature, recent papers, there is a possibility of continuous modification, because he was discovered these things in the year of 1954, and then of course you always know that science has no limit, so there is a limitations and advancements, so the research work is going on. So I have already, so today I will discuss the first method or second method or third method. All methods are available in the any good test book, and just you remember your first order, because if why I derived the simplest system first, because most of the books this method is very commonly available, and just you remember your first order kinetics, it is just like your A is equal to A0, if I am not wrong, or like that, exponential minus KT like that. Just do you follow this point? So it is exponentially, the initial concentration is exponentially decreased. But so the method is almost same. I'll explain these things. And I have already show you these 3 types of system. There are many also, but these are the very common system. Now this is the last transparency, then I will start the derivation. So this is the most important diagram, so you can understand these things. So let me start with this system, that This is the actual initial point. So you just, now this is going on, and by suppose T jump method, I am using T. This is common for all the method, T jump. So there is a perturbation. So initially it was, you can write X also, absolutely no problem, or X0 initial concentration, no problem. X you can call it, small x you can write. So when there is a perturbation, so naturally there is a new equilibrium. Okay, so that new equilibrium is x, you can write small x also, small x. It depends upon the different books. Now the difference between this initial and equilibrium condition is actually x is converted into xe. That is actually delta x, very small changes. And this is t is equal to 0 here, you can write. Now you can understand the difference between this, what is actually relaxation time. So what I told you that it is a return, that means I can color a new color, green. So this green part, so this green part actually, this is a new equilibrium. This is actually relaxation part. This is actually, you can call it as a delta x or x0 like that. This is actually delta x0. So this is actually tau value, the return from this. Sometimes we call it natural log of delta x0, delta x1 like that, or delta x0, delta x exponential. So I can define it, the distance from new equilibrium to actually original equilibrium. So that is called the relaxation time. So I have to determine this relaxation time. So this is the first part. Let me summarize that relaxation kinetics or relaxation type of the reaction can be studied with the help of T jump, P jump and E jump method. And most of the cases the time range is 1 into 10 to the power minus 6 seconds. And most common reaction is formation of 8 plus OH reactions. Thank you.